Welcome to Week 8, Session 2. First lecture, Lecture 8, Language Level Mechanism 1, Part 8, Monitor Definition. In this Language Level Mechanism 1, we will talk about monitor, and we have two parts, Part A and Part B. Let's get started. First, let's look at the semaphore. Semaphore's weakness. Semaphore is a set of the mechanism that help you to set up the critical section and with certain number of seats. So different process or thread can enter into the critical section. But it is a complex pattern of resource usage. So it is not easy to trace, especially when your semaphore statements scattered at different locations. So semaphore has limited seats, not an expandable queue. That's one limitation. Second, it's hard to trace back the code. Cannot capture relationship only with semaphores. Need extra state variables to record information, not a class. So it actually need extra variable, not actually tracking for certain class, and make sure that class is well guarded by critical sections. So semaphore has its limitation. So use semaphores such that one is for mutual inclusion around the state variables, that is the counters. One for each class waiting is hard to debug. So these are the weaknesses for semaphore. So in language level, we want to have something that's easier to use and that has the expandable queue, so you can allow many threads to get into the critical section, to wait on the critical section. So monitor is a language level construct to help you to solve these problems. But in fact, semaphore and monitors are actually very close. Some monitor can be implemented by semaphore. And actually, semaphore sometimes can be implemented by monitor, but it's actually a waste of time. Usually, semaphore structure is easier. Monitors are more complicated. So usually, semaphore is used to implement monitors. And with monitors, you can achieve a lot of different things. So semaphore is only a synchronization scheme that actually create a critical section and the management of the critical section with certain capacity and number of seats to allow different threads to get in. While monitor is a shared data class with operations and synchronization scheme, so monitor is a class with methods. And those methods can be implemented with synchronization schemes. And these synchronization schemes are born with the classes. A programming language construct that supports controlled access to shared data. This is the definition for monitors. Synchronization code added by compiler enforced at the runtime. Why does this help? So why does this really help with the monitors? Monitor is a software module that encapsulates a shared data class. So it's a shared data class with synchronization. So it encapsulates shared data structure, procedures that operate on shared data. So these are default settings for classes. And then they have a standard synchronization scheme between concurrent processes that invokes those procedures. So this is new, added to the classes. Monitor protects the data from unstructured access, guarantee only data through procedures, hence in legitimate way. So it's a legal way to do that. Now, let's look at the Java monitor. Java has data class, and every data class can be a monitor. So synchronized data class can also be implemented by condition variable. This can be implemented by condition variable or can be implemented by semaphore, but that's implementation issue. Now let's look at how to use it first. So for thread competing with resource, we have task 1 and task 2. And in task 1, we actually synchronize certain object. And this synchronized object actually is a shared data with operation and the wait and notified methods defined inside an object. So this an object actually is a object of certain class. So we synchronize on this object, and then we try this thing. And this one actually, while condition not met, we wait on it. So basically, here you are waiting for the entrance to the critical section, and here, when the condition is true, this is the critical section part. And this one actually is the one that will make the condition happen. Once it happens, you actually will notify it, and this process will resume. So this become a pair of the signal and wait pair, and you can have the cross signal and wait pair to create a critical section. So this is the way of synchronization in between the data classes or tasks. And this task can be measured in a certain thread. So wait and signal, notify, and the notify all are used in Java. It can be PV or wait signal in other languages. So these are the methods that have been defined in all the classes. And this is one example of two different methods in a runnable thread. How can they have the very low level synchronization? So example of using monitors, since we have the wait and signal, so we actually can use the consumer producer model. So this side, it actually, when this is capacity, actually, if it is count is capacity, this side is actually the producer. If it is full, then you cannot edit. So you need to wait until not full happen. And actually, if consumer side actually consumes certain integer from buffer, we will signal it, and then it will get into the buffer. And if it edit one element in, then it will signal the consumer to start to consume. So this is actually the producer-consumer model in Java format. And the signal and await, this different function name, you have to check the mechanism. There are several mechanisms in Java. So now let's look at the schematic view of monitors. So a monitor has the shared data and operation, just like any class. We have shared data, we have operation, and we have initialization call, that's the constructor. And these are the standard way of a class. But what's different is the entry queue that is new to monitors. A monitor is an object which edit mutual inclusive access feature. That is, you have those different methods, and also you have this queue. And stress queue is in OS or in Java virtual machine. Remember that we had a two-level implementation and maybe one-level implementation. So it all depends on what platform you are talking about and what is the implementation of the virtual machine or languages virtual machine, like Java virtual machine or Python virtual machine. It depends on the language. So not in monitor itself, it actually created by the synchronized in Java's case, and the queue can be in OS or Java virtual machine, depending on which level you are talking about. Actually, we talk about two-level implementation or one-level implementation. It depends on the implementation. Language level mechanism, monitors history. They were suggested by Edgar W. Dijkstra, and Dijkstra is a famous person, developed more thoroughly by Rich Hansen, and formalized nicely by Tony Hoare, a real cooperative effort. So it's not only one person or one certain invention. It actually are actually like a torch carry from one person to another, actually through many years to finish the monitor. And several parallel programming languages have incorporated monitor as their fundamental synchronized scheme, non-incorporate the precise semantic of Hoare's formalization. So Tony Hoare's version is very successful, but in fact, not every implementation will be 100% precise semantic of the horse formalization. But horse design will still be very valuable to study. Language level mechanism. A monitor is a shared object with operations, internal states, and a number of condition queue. Only one operation of a given monitor may be active at a given point of time. A process that calls a busy monitor is delayed until the monitor is free. On behalf of its calling process, any operation may suspend itself by waiting on a condition. So there is a waiting queue, and if you don't have the condition met, you have to be waiting for it, and your cell will be hanged in the process queue that wait on the condition. An operation may also signal a condition, in which case one of the waiting process is resumed. So it will signal somebody else to wake up. Usually the one that wait longest or on the first prioritized position in the wait list. Language level mechanism. The precise semantics of mutual inclusion in monitor are the subject of considerable dispute. Hall's original proposal remained the clearest and most careful described conditions. So these are the mutual inclusion for the monitors that described by Hall. It specifies two bookkeeping queue for each monitor, an entry queue and an urgent queue. So there's an entry queue and an urgent queue. When the process is queued, a signal operation from within a monitor, it waits in the monitor's urgent queue and the first process on the appropriate condition queue, but obtain the control of the monitor. So you enter into the critical session. When a process leaves a monitor, it unlocks the first process on the urgent queue, or the urgent queue is empty. It unblocks the first process on the entry queue is dead. So right here, it is a diagram for the this monitor. So we have the data object that we would like to associate with this monitor, and we have a special room. This one actually is accessing the data, and there is a wait set and there is an entry set. So this is like a doctor's treating room, and we have a lobby over here, and there is a person that actually being treated. So it's in critical session access controlled by mutual inclusive or mutex lock. So it is in here, and there are a certain people waiting, and they have been called by the nurse or the register that you are in the ready queue or wait list queue. And there are certain people, they have not been called by the nurse or the register, that you have not been admitted to the waiting list yet. So these are the three levels of the processes or threads. So first you need to enter into the clinic, and then you got called by the nurse or somebody who handled the administration, and then you got admitted to the wait set until you have the first prioritized. Then you got sent to the treatment room or the special room. So that is the way monitor works. It works similar to this doctor's situation. Language level mechanism. Building the correct monitor requires that one thing about monitor invariance. The monitor invariant is a predicate that captures the notion the state of the monitor is consistent. It needs to be truly initial and at monitor exit, number of items greater or equal to 0 or and less than the buffer size. So there are certain things you need to take care of. It also needs to be true at every wait statement. In Hall's formulation, need to be true every signal operation as well, since some other process may immediately run. Hall's definition of monitor in terms of semaphore make clear that semaphore can do anything monitor can do. So right here, as I show you, semaphore can do everything the monitor can do, and vice versa, monitor can do everything the semaphore can do. The verse is also true. It is trivial to build a semaphore from monitor, and that made no sense. But to build monitor from semaphore made more sense. But two, in terms of management power, they are the same. But monitor tends to be more easy to use and with more language definition constructs. So it actually well defined, but actually easier to use, but take more spaces. Semaphore is easier, but less definition and not easy to use. Right here, let's look at the bounded buffer case with monitor. So this is a monitor-based call for bounded buffer. So bounded buffer, we have talked about this already. It has the out pointer, out index and in index, and then it will add something into the in location for empty spot, and then it will take data out from the out index spot. So right here we have the monitor, and this monitor class is bounded buffer, and we have the B data, that is the data to be taken out, and the size of the bounded buffer. So we declare this bounded buffer data of this array that actually is the B data is a type. So we have the full and empty setting initial condition, full slot and empty slot condition. These are Boolean variable, just like what we talk about using the semaphore to implement the bounded buffer. The only difference is right here you have to wait for the bounded buffer. So this is the monitor. Other than that, it is similar, but it actually uses this wait and signal mechanism in this bounded buffer. And when it remove, it uses this wait and signal, and actually you will return after you signal the other process, and then you take out the data. So here we have the insert and remove, and it is using the wait and signal pair for the bounded buffer in monitor. And let's compare this with the semaphore version. The semaphore version actually has the insert and remove, and it has this P and V function. P is getting the mutual exclusive pair, and the empty slot and full slot. These two has the counter, and the counter set to 1 initially, so only one would be able to get into the critical section set up by this P and V function. And P is the entrance of the critical section. V is the exit of the critical section. So it actually will have the scattered pair everywhere. You can think about this as wait and signal, but it actually is more complicated. You can use the monitor wait and signal to implement this as well. But actually right here, it actually is the entrance and the exit pair. So it is more complicated. Let's compare with the monitor. This monitor version actually is easier. If the actually the full slot is equal size, that means you can no longer insert. So you wait for the empty slot. And then if there is a certain empty slot happening, you go in and put the data in. And then you increase the number of the full slot. And then you signal the full slot so that this consumer side can wake up. So this remove for consumer side, actually, it will also wait. If there's no full slot, then there's no data in the bounded buffer. You have to wait until you have some data in, and then you take it out, and you signal the producer side, the insert function, that you actually take out something, and then you can insert some data in. So these are pairs of the producer and consumer pair implemented by the monitor's wait and signal pair. But in fact, this bounded buffer can be implemented by both semaphore and the monitors. Now, I'm going to talk about language level mechanism. Part 1. Part B for monitor implementation. In this lecture, we will talk about semaphore, condition variable, and the monitor. These three are very close, and actually one can implement the other two. So they are closely related. So we actually talk about these different implementation issues together for semaphore, monitor, and condition variable, but they have slightly different feature and different purpose. First, let's look at the implementation for semaphore. The usage of semaphore is like this. You declare a new semaphore mutual exclusive access. Then you can have the wait and signal for the mutual exclusive access, and then you enter into some critical section. This is the use for semaphore. That's easy. To implement that, you actually can implement the wait function with certain semaphore variable. And if it is less than equal to 0, no, you have no up, and you actually busy waiting here until you got some seed, and then you decrease it and you enter into the critical section. And the signal part, you actually, when somebody leave the critical section, you can actually increase the number of seed available. So these are actually quite simple. So S or count, keep track of how many remaining seed allowed to enter into critical section. Initial condition of S, keep track of the maximum number of seed in the critical section. That's the capacity. So semaphore is designed with certain capacity. Wait and signal are not always paired. Maybe more signal executed than wait. Then the maximum number of seed will be increased. Monitor. Now let's look at monitor. Monitor can be implemented by semaphore, and monitor is a program concept or data structure concept, and semaphore is a data synchronization concept. So they actually are different. And semaphore can be used to implement the monitor. And the monitor would have these following different global variables: mutual exclusive, next, and next come. Mutual exclusive is a semaphore that initialized to 1. So it only allows the capacity of 1 to enter into the critical section. It is used to control the number of processes allowed in the monitor, the critical section. So let's go back to the previous lecture. For this chart, actually, that mutual exclusive count will be the capacity in the spatial room. And we have a next, and this next semaphore is initialized to 0. And remember that we may have more signal than wait. So this number can increase. It is used for the waiting queue by the process that are in the monitor after being released from a conditions queue by signal operation. So this is the waiting queue. And this waiting queue is the one in this wait set. And the next one is next count. It is a integer variable initialized to 0. It counts the number of processes sleep on the next semaphore. So it is always equal to the number of processes executing the monitor operations minus 1. So it's from 0 to n minus 1. This is a complex way of saying that only one process at one time can be actively executing within the monitor operation. This is called the active process. The processes waiting on the next is the inactive processes. And to implement a monitor using semaphore, we can have the entrance call like this. We will have the waiting for the mutual exclusive function or entrance of the semaphore function for mutual exclusive semaphore. This is the entrance call when starting execution of a monitor operation. And the exit call is like this. You have the next count greater than 0. That means you actually have some sleeping process sleeping for the next semaphore. So the next seed. And then if it is more than 1, then you actually signal the next waiters. So signal the one in this room, this waiting for the doctor's room. And if not, then that means that there's nobody waiting in there, so we wake up the general public. And this is the mutually exclusive part. It will be this entry set. So that's the three set we have. So these are the entrance code and the exit code to a monitor using semaphore. We actually have this entrance code for mutually exclusive, the signal code or the exit code for the semaphore mutually exclusive, and we also have the exit code for the next queue. And the next queue can have 0 to as many as possible number of the waiting set. So this signal can be many. If it doesn't wake up the mutual exclusive, it actually will wake up the one in the mutual exclusive set, and then you got +1. So somebody would enter into the waiting queue. So if there is no wake up call, and if there is somebody waiting there, we will wake up this one in the waiting queue. So P of X is equal to wait, and V of X is equal to signal for the semaphores. And actually, we have two different kinds of semaphore, one for the next queue, one for the mutual exclusive access. So to implement the monitor using semaphore, if we have a synchronized method like this, it will be compiled to the following thing. The data structure will have the semaphore mutual exclusive, semaphore next, and the integer count, next count. And the integer next count equals 0. And then for this synchronized method, we will put the entrance code here, the exit code here, and then you put your function body over here. So this part is the P function for the monitor, and this part will be the V function for the monitor. So for the real application, we can have a instant synchronized method like this, or this. These are two ways to write it in Java. And we use the synchronized method in class. Mutually exclusive access in the method. Wait and notify are available in the synchronized method. And this wait and notify actually are this session and this session for P and V. So when we implement the bounded buffer case, we have a buffer, we have the count in and out, and we actually initialize the bounded buffer with certain size. And then we have the put, this one is the producer, get, this one is the consumer, and we put a wait and signal pair right here and here. And this wait, when you implement with the semaphore, this will actually behaving like the semaphore wait. But if you have this synchronized method for the Java monitor, this wait and notify pair will be behaving like the monitor case. So they will be implemented like this, the P and V function here. And actually, in the background for the monitor, we have this data structure as well. So that's the way that Java is implementing the bounded buffer for us. And actually, the notify and wait are the P and V function. Sorry, the wait and notify function are the P and V function for the monitors. And the monitors can be implemented by the semaphores. And a synchronized class method is like this. Instead of putting this, you put myClass.class. And this is equivalent to static synchronized void my method. So we have told, and so here I have shown you the instance synchronized method and the class synchronized method. Monitor feature, Java has built-in monitor feature, C don't need to use pthread library, and pthread library is available for Linux. Condition variable, let's look at the condition variable implementation. Condition variable, it is improved from semaphore with thread in queue. Semaphore had limited number of seats. Condition variable has a queue, so it has a flexible length of the queue. Consider an operation system. An idle request from a user program via a system call may not be completed immediately. Say we try to write something to the disk, and the writing head may be waiting for different process to finish. Should this happen, the operation system may postpone this I/O service and serve another user until the I/O operations completes. Then the operation system will resume the I/O service for your program. In this case, the user feels that he is blocked within the operation system. For a similar reason, a thread in a monitor may have to block itself because its request may not be completed immediately. This waiting for an event to occur is realized by condition variables. So condition variable is to implement the waiting for events. Condition variable. A condition variable indicates an event and has no values. It has no value. It only has the methods. More precisely, one cannot store value into nor retrieve a value from a condition variable. If a thread must wait for an event to occur, that thread waits on the corresponding condition variable. If another thread causes an event to occur, that thread simply signals the corresponding condition variable. Thus, a condition variable has a queue for those threads that are waiting the corresponding event to occur to wait on. And as a result, the original monitor is extended to the following. The private data section now can have a number of condition variables, each of which has a queue for thread to wait on. So basically, we can have a monitor, and the monitor actually is guarding on the mutual exclusive access for a certain class. And we can add some conditional variable to there, and conditional variable has its own queue. And these conditional variables can be used to monitor the conditions for the I/O channels. For example, we have a monitor on certain data set, and we have the I/O channel condition variables. So each control variable is associated with a resource, usually maybe it's I/O or disk. A monitor class is a resource. The condition variable works like semaphore, except that it has a queue. So the length of the queue is flexible, but semaphore has fixed number, which it is specified by the capacity. And other than that, it is similar to a monitor class. So right here, I show you the diagram for condition variable by semaphore, and you have shared data, and you have queue associated with the SY conditions, and you also have a queue for the monitor entries, and you have operation and initialization call. So it is similar to monitor or thread or event queue, and you can declare condition variable X and Y. Two operations on a condition variable. You have the wait and signal similar to the semaphore, except that they have a queue. So their waiting set is undefined, can be 0 to as many as you can. So x.wait is a process that invokes the operation to be suspended. X.signal resumes the process that invoked by x.wait. And here is the implementation for the condition variables. We actually have a condition variable, and then we have semaphore, sem, and integer count. These are the data structure need to be associated with a condition variables. And then we have the wait function like this and signal function like this. This is the P function and V function for condition variable. Remember that it can also be implemented by semaphores, and it would achieve the wait and signal function for condition variables. And condition variable can have a queue, and these are similar to the monitors. And you can actually implement a monitor using condition variable with such data structure and with such wait and signal function and declaring a variable conditions. Implement monitor using condition variable is just like using the semaphore, except it has a queue, and the weights and signal function are like this, and adding the data structure in there. Lecture 10, Language Level Mechanism, Part 2, Condition Critical Region. What is Conditional Critical Region? Conditional Critical Region, CCR, are another alternative to semaphore. A critical region is a syntactically delimited critical region. A conditional critical region also specifies a Boolean condition which must be true before control will enter the region. So we have protected variable and a Boolean condition. Once the Boolean condition is met, then we enter into the critical region. So compare with the semaphore actually checking certain condition or the number of seeds to be met before you go into it, and you have a class or something that is actually being accessed by the monitor. And semaphore don't have this protective variable, but this is similar somewhat to semaphore or the monitor. No thread can access a protected variable except within a region statement for that variable. Regions can nest, though as with nested monitor codes. The programmer needs to worry about deadlocks. So you need to care of the deadlocks in using the conditional critical region. So right here we have an example of using the conditional critical region for bounded buffer, and it is quite straightforward. We have the same record, same setting for the next full and next empty, and same setting for the floor slot. So right here, when we check on the protected variable buffer, that is a queue, and then we check if the full slot less than size. That means you can still insert the data, so you get enter into here. So in conditional critical region, you don't have the weight and signal pair. Instead, it is implemented by a region statement. Similarly, for this remove function for consumer. And you have the access condition and protective variable set up like this. But the algorithm is similar to semaphore, monitor, or condition variable. Right here, we show you the conditional critical region and a statement right here that is called atomic. And when the condition is met, you go into the statement. This is quite simple for the pattern. So wait until condition is satisfied, execute the statements automatically. And right here, we have this get function for queue. If the items not equals 0, then we decrease the number of items and get the data out. This just like the popping of a stick or getting an item out of a buffer. The implementation of conditional critical region can be done by software transactional memory, and software transactional memory will be covered later in a separate lecture. Right here, I just show you it can be done by this software transaction memory. Use all traditional STM command and STM wait, like implementation of monitor using semaphore. Implementation of conditional critical region can use software transational memory as M. So the statement right here, you put a condition right here and statement right here, and this will be the implementation for this CCR, the conditional critical region. So you have the condition map and you go into there, and since this statement can be done, so we actually make sure that the transaction is committed. Otherwise, if the condition not met, then we wait on the condition to be met. And if there is an exception, for some condition you wait, then you wait for it until it is done, you store the T. And actually this storing T will be handling some exceptional condition that may happen to your conditional critical region. Language level mechanism part 3, synchronization in Java. We have a complete video tutorial over this website. I have these tutorials and it is free for you. You can come to this tutorial, but somehow I have not finished this tutorial completely. So if you go there and didn't find all the lectures and quizzes, you can just wait. And actually, I will make it up soon. And actually, for the time being, it probably only has 3 lectures, and I plan to go for 13 lectures for this tutorial. Synchronization in Java, we have thread, future, and callable classes, and the related pools. And we have semaphore class and the new condition class. Semaphore is for normal semaphore, and new condition is for condition variable. And we have lock, re-entering lock classes for mutual exclusive lock. And we have semaphore using semaphore class, monitor design using the synchronized keyword for lock variables. And we have conditional variable. We have condition variable using new condition class. So apparently, most of the mechanism being implemented in Java. Core example, we have the critical region. We use the synchronized method, and we actually put the object over here, and this become a critical section. And we can also use the lock variable by declaring a lock. And we have the lock and unlock pair. This just works like the mutual exclusive access control for lock and unlock. And we have semaphore. You can declare a semaphore, but the semaphore will have the acquire and release. This is different from the traditional name of PV or wait signal pair. The name for semaphore methods actually are acquire and release. For core example, for condition variable, you can declare a condition, then you have the condition wait and signal statement like this. And if you want to build a monitor, you can have a simple monitor, and you have the lock, unlock using the re-entry lock, and you can replace the lock, unlock with the semaphores acquire and release, or condition variables wait and signal. And or you can also use the monitors synchronize the critical section like these statements. The instant synchronized statement that can also implement for the monitors. The Java memory model. The Java memory model specifies exactly which operations are guaranteed to be ordered across threads. It also specified for every pair of read and write in the program execution whether the read is permitted to return the value written by the write. A Java thread is allowed to buffer or reorder its writes until the point at which it writes a volatile variable or leave a monitor. At that point, all its previous writes must be visible to other threads. Similarly, a thread is allowed to keep cached copy of values written by other threads until it reads a volatile variable and enter a monitor. At that point, any subsequent read must obtain new copy of anything that had been written by other thread. So Java memory model actually rely on the cache coherence model, and actually some variable can call as a volatile variable, and we need to take care of it. The Java memory model, the compiler is free to reorder ordinary reads and writes in absence of intra-thread data dependence. If the compiler can prove that a volatile variable or monitor isn't used by more than one thread during a given interval of time, it can reorder its operation like ordinary accesses. Volatile is related to write-back scheme. So basically, this is how the Java memory model is implemented. Now, let's look at the language level mechanism part 4, transactional memory. Transactional memory, the software's transactional memory is used to implement the conditional critical region. Software transactional memory, actually software means the algorithm, transaction means data baseline, and memory means data access. So you actually have the algorithms for database-like data access to your memory. And database-like means you had a mutual inclusive access to the database, and same thing for the memory. And we have the software transaction memory as the protocol to access a memory with the mutual inclusion. So STM usually is a language extension or API framework. It is just like another concurrent control mechanism like log, actor, semaphore, condition variable, or CCR. So STM is another protocol. ACID. For database, we have this word ACID. A for atomicity, C for consistent, I for isolation. And database require your read or write to be atomic. You cannot break it. And data need to be consistent. And the critical region need to be isolated. And also the data need to be durable. So it has the durability. But for STM, since we are not saving the memory back to hard disk, it is only in memory, so we don't have the durability issue. So not for database, it is actually for memory transaction about this red cross. So this red cross is not for database, it's for STM. So transactional memory used to implement conditional critical region. Transactional memory attempts to simplify concurrent programming by allowing a group of load and store instructions to execute in an atomic way. So basically, this is a load store operation that actually is handling the CPU and the memory. It is a concurrency control mechanism analogous to database transaction for controlling access to shared memory in concurrent computing. Transactional memory system provide high-level abstraction as an alternative to low-level thread synchronization. This abstraction allows for coordination between concurrent reads and writes of shared data in parallel system. Hardware transactional memory. We have hardware transactional memory just like the cache and database. And actually, this is a special hardware. You have the on-chip connection bus or network, and you have the data cache, and you have the concurrency, and you have the coherence request, and access the transactional memory register, user register, and register checkpoints. So basically, this transactional memory can be implemented by hardware. But how transactional memory works, we will look at the following slides. A simple idea to think about transactional memory is like this. You have the hardware transactional memory, you have transaction routine, you have transaction runtime, and you have throughput cache and shared memory. So these actions are working on the cache, and cache will have the coherence problem with memory. And similarly, for software transaction memory, the function or algorithm you talk about is transaction descriptor. And the records that before writing into certain object is called ownership record, and it is similar to cache. And the shared memory for software, it is actually application heap. Transaction memory management, you have this method, STM start, that will begin a transaction within the executing thread. STM abort, that will abort the transaction progress by the executing thread. And actually, this is what it means. When you try to write something to the memory location, and actually you cannot hold a variable or record to write it, then you will have STM abort. So this actually is write miss or wait signal. And we have the STM read and write. These are two transactions. And we have STM commit. And this commit means write hit. That actually will attempts to commit the transaction in progress by the executing thread, returning true if it succeeds, and fail and false if it fails. Software transaction management, we have STM validate. This is a Boolean function, and you will return whether the transaction will be validated or not. It indicates whether the current transaction will be able to commit to be executed or not. That is, whether the value read represent the occurrence and the mutually consistent snapshot, and whether any location updated have been subject to conflicting updates by another transaction. STM wait, the sleep and wait on signals, and STM wait would be equivalent to STM abort, leading to caller spinning waiting. In our implementation, STM wait blocks the caller until an update may have been committed to one of the locations that the transaction had accessed. So STM wait is similar to the STM abort. So wait is more popular term actually. And right here is a pseudocode for STM system. And instead of reading this pseudocode in detail, let's look at one example. So right here is a simple STM transaction. We start the STM service and read value. And if we can write, we check the STM validate. So this actually is the wait signal. If it is validated, then we go in to do the transaction and perform the STM commit. And if it is done, then we break. And this break will break the whole loop. So right here, we have the application heap. This is like main memory. We have these records over here. And we will pairing algorithm with this. So we have the ownership records, and ownership record is just like a cache. And this cache will keep track of the current versions for each of the record. And one of the record may have 2 entries. And then we have a transaction descriptor 1. This is a transaction that will make modification on the ownership record. This work like cache. And the other one, we have application heap. This work like memory. So we have 2 transactions. We will modify the A1 from value 7 to 7 and version 15. And we will modify A2 record with version 7 from 100 to 300 to, and that 300 is version 8. So basically, we decided these 2 will be modified. And then we commit it. And then we commit to modify it. So the value for this heap, for this record A2 becomes 300. And the version being updated to 15 and 8. And when will the abort happen? So we are trying to commit the write to these 2 records. And if at the same time, we have the transaction descriptor 2 also request to make the modification, then this same version 8 won't go through. So A2's ownership record is unavailable, and commit, fail, and abort. So this one will be waiting. And STM collision, when you have the STM collision, you have STM abort or STM wait, then we will be waiting. And actually this time, for example, we had such A1 update and A2 update, and we have this transaction sharing the same destination. So this one actually will be kicked out. So this program failed my CCR condition, so I aborted and fell asleep. And then this part 1 committed to update the memory for location for A1 and A2. And for description, for transaction descriptor 2, it will be waiting because it is locked up by some other process. And when we optimize it, we can move up to here. So basically, we have A1 transaction that is committed to this A1, and for the value from 7 to 7, stay from 50 to 50. And A2 will be related to this record, and actually it will be modified from 100 to 300. And we have the A3 transaction that will write this A3 from 200 to 8, and the version updated to from 8 to 9. But this is inconsistent with the A2 transaction. So we actually can optimize it by stealing the original record from this descriptor 1 to move on to descriptor 2. By this way, this transaction 2 can still be used. And STM and HTM parallel the data copies. So here are the relationship between HTM and STM. Now, we are on the last lecture for chapter 13, language level mechanism, part 4, other topics. The first other topic, implicit synchronization. Actually, this is an isolated topic, so we will go on this first. In several shared memory languages, the operations that threads can perform on shared data are implicit rather than explicit operation. That means you have some language structure and you will initiate several threads instead of having the implicit operations to call the threads or initiate the thread. For example, the for all loop of HPF and the Fortune 95. For all loop, each iteration reads all data in its instance of the first assignment statement before any iterations updates its instance of the left-hand side. The left-hand side updates occurs before any iteration reads the data used in its instance of the second assignment statement. So basically, if we have a for all loop, and then we process several additions for each of the element pairs, so X1 will plus with Y1 and produce the result of G1, we have such vector processing for each of the elements in X array and Y array. But our processor can handle up to 4 in parallel, so each time we need to have one block being processed. So initiating these threads are implicit instead of explicit operations, and explore the maximum vector parallelism in dataset, processing unit, and compiler technology. Dependency analysis plays a crucial role in other languages as well. So basically, you have to count how many threads can be run in process, and that we can unroll your loop in the for all loop in a way that will explore the maximum vector parallelism. And this is done implicitly. The second topic I'm going to talk about is the future. But before we touch this topic, let's look at something else. For those of you who did not sign up my concurrent programming course for Java, please do so, because there is a lot of very important information. Before we move on, to the future, let's look at the thread class. A thread class is a manager for a thread. And in the thread, we can put in a runnable object. And this runnable object actually can have a run function. So this thread will run on the function that's specified within the run method. And this is how we manage the thread class and having it to do some calculation. So the idea is you have a thread, but the task you want to perform should put in this run function. And this run function will start when somebody calls the start function in the thread manager. And the thread manager is a container that contains the runnable object, and the runnable object carry the code. And there are several different methods to be used for a thread. And this thread option can work on several different functions as long as you put different functions into the run function. And the thread can also perform the fork and join operations. So basically, you can create certain thread, and the thread itself can fork some process if you actually initiate a new thread inside a certain thread, and you initiate this new thread 4, and you get started with the over there. And at a certain point, you can join the thread 4 into the main thread, so that will be joined over here to finish this one and go back. And thread also control the states of the thread. For each thread, you will have the run state, a ready state, a running state, and the wait states. Let's return to our slides. Thread is related to our topic for future. Let's move down for a couple of slices. Let's look at this first. The thread is a wrapper for runnable object, and runnable object actually has a run function but have no return value and no exception. And you can have a version that is callable. A callable object has a return value v and can throw the exception. So that's a different version of the runnable object. We call it callable. So when you call, you have the return value and can throw exception. But if you run, that has no return value and no exception. And the wrapper for callable object is called future, and the future actually will return some value that is passed from the callable object that will be put into the future task. And the relationship of the callable and future is the following. You have the runnable interface, and you have the future that is the interface, and you also have a runnable future that combine these two interface, and then you have future task. And future task can call a runnable or callable. So actually, future task is the concrete class that can call runnable and callable. And thread, you can only put the runnable over there. So that's the difference. So future, important point, future and future task in Java. Future is a base interface defined abstraction of an object which promises result to be available in the future, while future task is an implementation of a future interface. A future is a parametric interface, and the type safe written as future v, and v is the value that you can return, and actually that will get from the callable object. And callable object is the method wrapper for future task. And future provide get method to get a result from this for this v value, which is a blocking method and block until the result is available to future. Future interface is also defined. Future interface also define cancel method to cancel task. So future actually is a manager for the task, but future is an interface, the real manager object or class or concrete class is the future task. And you also have the is done checker, is cancel checker, something like that. So let's look at the future and callable in our Java language. So this is in my tutorial. And the difference between runnable and callable is parametric. You can put different type over there, and that type actually is the value that you will return when you call. And the call function is similar to run function, except that run function, you put the call in, but you don't return value, but call function, you can return the value. And then runnable cannot throw the exception, and callable can return the exception. So right here, we have one thread that implement runnable, and the run function just print out Java welcome or well. And over here, you actually can throw the exception, also had a return value, and that will be returned in the string format that is callable with the type variable string. So right here, we have this same summary page. Let's move on. And callable is runnable in multi-threaded procedure. Callable is multi-threaded function, and runnable is a multi-threaded procedure. That's the difference. And future is the object. Future object is a handler for runnable and callable objects. So future or future task can carry runnable and callable, and thread can only carry runnable. So future is an interface. Usually it is not directly used. Runnable has limited capability. Future has method to receive the value called .get. Future has a method to check the executor is done or not. Future has method to cancel its executor. Future has a method to check if the executor is canceled. Future is combined with runnable and runnable feature to have complete features. Future can submit a runnable executor, work like fork. And future, you can run and get value and return. So runnable future and the futures relationship are here. And string worker is for the string AWT package. But these are not covered in this chapter. But basically, you can see future task will be able to run runnable and the future, and it is the concrete class. And I is actually the interface. And this is the environment for runnable and the future and the executor. And these are the detailed framework for executor framework interface. I don't want to go into the detail for this, and this is part of the tutorial. Let's return to our slides. So roughly say, callable and runnable are methods these callable and runnable are interfaces that can have the methods that carry the call, and call function has the return value, and future task and the thread are the carrier or the wrapper for callable and the runnable. And future task can wrap up callable and runnable, but thread can only wrap up runnable. So the future in multi-Lisp. Implicit synchronization can also be achieved without compiler analysis. Future construct a dialect of scheme. So by future, actually, you have some function and arguments, and actually you branch out a certain thread. It is called future. And future is semantically neutral. Assuming all evaluation terminate, a program behavior will be exactly the same as this, except that it is branched out as a separate function. In the implementation, future arranged for the embedded function to be evaluated by separate thread of control. So it has a separate thread. So you have a parent process, you have one child function. second child function is put into two future wrapper. So these two actually run as parallelly, and then the parents will join them together. There were no additional synchronizations mechanism in multi-lisp. Future itself was the language-only addition to scheme. And future in C#. In C# with parallel fx, we can use future to create a task. And this future has a lambda expression, that's the function being put in. And after it finishes, it will return the value to discretion. So same thing for this number in stock. It calls this function, and the value will be returned to number in stock. So these are future functions, and we actually will get the value once the process finishes. And static feature is a factory. It creates method support generic type interface inference, allow us to pass delegate compatible with function t. So you actually can put certain function in there. Something like lambda expression is okay. For t, we have specified the delegate here as lambda expression. If get discretion return a string, discretion will be type future string. If get inventory return an integer, number in stock will be type future integer. And we have done this. And we have done this as well. And we have done this as well. So future is important point for future and future tasks in Java. Future have 4 sub-interfaces, each with additional functionality: response, runnable future, runnable scheduled feature, and the scheduled feature. So these are different type of features. Runnable feature also implement runnable, and the successfully finish of run function cause completion of this feature. Future task and swing worker are two well-known implementation of future interface. So these two are concrete classes that implement the future interface. Future task also implement runnable future interface, which means this can be used as runnable and can be used as callable as well, and can be submitted to executor service for execution. And executor service is a pool of runnable object or task. Though most of the time, executor service create future task for you. For example, when you submit callable or runnable object, you can also create it manually. Future task is normally used to wrap runnable or callable object and submit them to executor service for asynchronous execution. So future task is a wrapper and can submit this function to the service, and the service is a pool to allow you to accept several runnable or callable object over there. Topic, we are out of the future now. Topic, parallel programming, parallel logic programming. There are two strategies for the backtracking, searching of logic language, such as Prolog. Is also amendable to parallelism. One is end parallelism, the other one is or parallelism. The fact that the variable in logic once initiated and never subsequently modified ensure that parallel branches of an end cannot interfere with one another. So basically, in logic processing, in logic programming, we have end parallelism, so you can run several end at the same time. And you can also have or parallelism, so you pursue alternative solutions in parallel, because they will generally employ different unification branches, or branches of an or must use separate copies of their values. So this is the parallel logic programming. Basically, you can pursue two types of parallelism in logic programming. End parallelism and or parallelism create new thread at an alternating level. Or parallelism is speculative. Since success is required on only one branch, work performed on other branches is in some sense wasted. So actually, or you have to, or sometimes would over execute it because it will waste time on something that is not necessary. All parallelism work well, however, when the goal cannot be satisfied, or when there is high variance in the amount of execution time required to satisfy a goal in different way. For example, you cannot predict the execution time of a certain branch. Both and or parallelism are problematic in Prolog because they fail to adhere to the deterministic search order required by language semantic. Prolog, which supports both and or parallelism, is best known as the parallel Prolog dialect. Message passing. Message passing is not covered in this book, but message passing is more useful in multi-programming, and shared memory model concurrency is more useful for multiprocessing. For a program in the same computer with a shared model for different processes, but message passing is better for different programs to share the data or perform the synchronization. Shared concurrency is becoming ubiquitous on multi-core processor and multiprocessor servers. Message passing still dominate in both distributed and high-end computing. Supercomputers and large-scale clusters are programmed primarily in Fortran or C++ with the MPI library package. MPI means message passing interface. Distributed computing increasingly relies on client-server abstraction layered on top of libraries that implement the TCP/IP Internet standard. As in shared memory computing, scores of message passing language have also been developed for particular application domain or for research or pedagogical purposes. And we are not spending a lot of time on this message passing right here. Thank you, and this concludes our chapter 13 and also conclude our discussion on this textbook for our 8-week course. I really appreciate your participation on this course. Thank you, and I'm looking forward to have a chance to be with you sometime for other courses. Thank you. Bye.